Welcome back to Cloud Computing and Big Data, Lecture 12 on Docker and Container Management. The last time we talked a little bit about basically really using applied machine learning in cloud computing, using data mining techniques, recommender engines. And the topic of today is really supporting this in many ways, although it's really hidden to the end user in many cases, but enormously enables flexibility really of deployments. So also before we touched base on Docker, when we had MapReduce in one of the earlier lectures, if you remember, where we said we need to have something pre-configured in terms of software and something which is a little bit different than virtualization. And I think this lecture will share light on this particular fact and also will actually then compare several aspects of this, basically what is container management compared to virtualization. But before we dive into the material of this lecture today, please, let us review a little bit what we did the last time. And we said there's a certain kind of association rule mining that Shadi in his lecture 11 already introduced, and we want to execute it in the cloud. So of course, for that, we need particular packages. And one of the packages we installed there in the last lecture was really this MLX10 package that you see essentially here, that you nicely can actually use in the Jupyter JSC environment, which was a Jupyter notebook and a Jupyter lab environment, really, hosted in this so-called HDF cloud in the Helmholtz Data Federation cloud. With this, you see also an example how you can create cloud solutions on your own. You don't have to be Amazon, you don't have to be MS Azure. And one of our next lectures, when we talk about OpenStack, will explain you a little bit how you can create your own cloud, basically, as a computing center, or perhaps even as a big company where you think that AWS services are maybe, too costly. You remember one of the slides from Rocco where he shed lights on the fact that actually doing deep learning here and there in AWS could be really costly if you have, let's say, very big cutting edge models in deep learning. In this sense, this was a good example of showing you a different cloud, and it's also part of your assignment 3. We learned essentially that the association rule mining, however, has, let's say, certain drawbacks from the general approach speaking. It's not personalized, right? And this is a big disadvantage here if you want to look today in so-called recommendations or, let's say, insights from data mining for shopping behavior as an example. You always have a general shopping list. You don't have a personalized information who bought what alongside it. However, you will see that in many stores we work with, we have seen the PAAS store for, let's say, perfumeries and beauty stores and so on. This is just one example of shops like supermarkets and so on, like fuel stations, whatever. They all can still benefit because many people don't really use these algorithms. And this is a surprising case also for us in research in Germany in one of the projects that Shadi was alluding to with the on-for-off project, for example, where many people still don't take the message. They haven't got the message that data is value, data is gold about your customers. They didn't take the value that machine learning can be really applied quickly without doing too much math. Math is important, but many of the algorithms are relatively easy to understand, like the a priori algorithm that in the end builds a lot of the support ideas. So how many actually are there in the transactions? And with this, you quickly come to an algorithm that is, let's say, relatively easy to understand, at least in the singletons or doubletons. We said also that when you go to certain levels deep here, where let's say a 3-item set, for instance, that bread, milk, and diapers will be always brought together, might be also something that, a human mind don't really grasp anymore, especially if it's not, let's say, this traditional elements in a supermarket, but maybe in a beauty store. But we also took away the fact that the way how you approach the problem, how you encode it is, of course, also a complicated issue and relates to compute time, because in the a priori algorithm, you remember we had this one hot encoded data structure, which essentially takes on the shopping list that we have here and then creates a very big matrix of saying essentially what was bought and not bought, essentially in a one big matrix, if you want. And of course, this is a little bit cumbersome if you have millions of transactions. So you have a very big matrix, a data structure, which is in one hand, of course, okay, but there are better algorithms for it. And we learned this, that instead of using the a priori algorithm that is taking away this data structure for solutions, we can use, for instance, the FP growth algorithm along many others. Actually, there's Mafia, there are different algorithms, but we use the FP growth algorithm that is also part of your assignment and actually also implemented in the ML extend. And the benefit is here really to leverage the properties of tree data structures, which in computer science are always, let's say, a very powerful infrastructure for data, for using data, for reusing data really, which is an important factor here. And with this, you come to a much better runtime that you hopefully also explore in the assignment. And then basically we had different measures of trusting that data that you created. We said there's antecedents and consequence. So a certain level of confidence that you have to do. There's a support, while confidence really shows you how often this rule that, let's say, eggs and cheese will be always bought together, is basically is true, is like here 0.68%. So you would trust that much more than maybe other rules that you have with lower values. And there are many others, and we discussed them in the last lecture, so I don't go into the detail. And of course, the same measures are true absolutely for the FP growth algorithm, because it's in the end, it's the same algorithm in a way for searching association rule mining in an unpersonalized way. We also learned that exactly this could be a hindrance. So there's better algorithms for some recommendations if you have personalized information. And we learned that this is recommender engines. The field is very broad. Here we see an example of collaborative filtering, where you essentially have a matrix and matrix dot product and try to, let's say, get to something close that you already have, which would be the ratings of a movie, let's say from 1 to 5. But if you don't have that, it's still enough information that you maybe look the movie or not. And of course, the movies are just one analogy. You can always have, let's say, all other products. Important is that you have this matrix that you know who, so which personality was looking which movies or was buying what products. And with this, you have a connection, you have a personalized information. And this is, of course, let's say, gold again for the stores. However, our practice reveals that actually less people or less stores really applying this technique, which is surprising. I mean, there are many reasons for it, like data protection principles, but also people have not realized that rating products after purchase can be leading to lots of insights over the course of 5 years. If you do this and have ratings, because you're essentially also not really allowed to crop all the ones from Amazon and steal them, so to speak, and use them for your own procedures. So in this sense, this is really something where these techniques are tremendously good. We also said last time, they come also with some side effects. You would say, for instance, if you have looked just 2 movies out of 30,000 movies maybe that are in these online streaming, let's say, offerings, this is not enough. So basically here you have seen a certain number of movies, that's important. But if you have done so and have a matrix that is, let's say, really not completely, let's say, filled, it is unthinkable that this would happen. But at least having, let's say, something like a good order of films looked at, then you can start and getting basically these hidden kind of embeddings that you learn. So these are these matrices that we don't know in the beginning. Only that we know is this, of course, key metrics here, which is, let's end basically our ratings. And if you want 0 and 1, if you looked or not looked the movie. And the idea is here to really try to learn essentially, and we have seen last time, it could be transformed to a minimization problem, an optimization problem in this regard, in actually getting this dot product of these 2 matrices to something very close to what we have already in our given data set. So we have, let's say, an error measure we can always have, let's say pointwise error to all of these different entries. And over time, the optimization will take care of getting close to it. And with this, you kind of reflecting a little bit the personality on the one hand on this side, and the movie content perhaps on this side, also the key properties. Although, of course, it's hard to say. So that property 2 is 0.9 allows us here to say that Harry Potter would be very important in your case. Of course, what you would recommend then would be the wholes of this. So you would say, we will find something where the value is relatively close to 1, because this would be perhaps a grown-up movie, and other way around. So this is something which really works in practice a lot, but also, of course, can benefit from big data, can really, leverage if you have lots of different ratings. And one of the key ideas is, of course, to also think about this in your assignment when you do your practicals in the Google Colab, but essentially saying that, you have seen it with Shadi in his presentation also, he is just deriving the script and actually reusing many different elements of it in order to do something for a beauty store. So it doesn't have to be movies. It doesn't have to be the people that watch movies, but you can transform, let's say, the initial idea of these recommender that you learn about also for many different situations. And also you will see essentially that you have always this crisp DM process. When you, let's say, do this in really practice, you try to understand the problem. Then you have a certain data understanding, will understand, do we have ratings here from 0 to 5, from 1 to 5 or whatever? Or do we have just the movie seen or not seen? So these are different data understandings. Then you would prepare the data. Here you see we have to transform that a little bit into a more numerical situation from this embeddings here that will in the end then be learned. From this idea to having a dot product, which is then, of course, a numerical interesting matrix here. And if you do so, you do some modeling, which is in our case and the collaborative filtering, basically trying then with matrix factorization, really what you see here, in order to come up with the key metrics, which is our given data set. So in a way, it's a supervised scenario. We know the solution. We can always say for each of the cells how good we are doing, because in the end, we should have values that reflect the situation if we've seen or not seen a movie. And when you're satisfied with your evaluation, you go to the deployment, maybe in Netflix, maybe in Amazon Prime. But if you're not satisfied with the evaluation, you maybe even start with a problem understanding, go back and say, maybe we misunderstood things, or you go back maybe to the modeling to some data preparation, use another modeling technique. You have seen that alone the recommender world is having, singular value decomposition. You can go on and on. There are different, very much approaches for doing recommender engines today. It's like would be worth a whole lecture series just on recommender engines. And if you want to dive more into details from matrix factorization and different approaches. But that's basically a little bit what this basically assignment of yours also should be reflecting. We will pick here one approach, which is this matrix factorization approach. And you see alone for that, it's quite interesting to apply different aspects of tuning those and looking on the data quality. You remember we had the idea that drama was basically very much more looked at than any other category. So we have some bias in the data. We have to fight this. We have to work against this. We have also, of course, a certain number of people watching. And you have seen the last time the students were extraordinary much in looking videos or movies, while all other professions actually don't look movies very much like students. So this gives you another bias, of course. And then when you create a recommender engine, learning from all of those, and you don't take care of these biases in the data, which should be an assignment, basically providing you some grounds. The last assignment too was more on regularization validation. Now we talk about data quality, data preparation, and in different ways, really cleaning the data or basically balancing the data to have class balance and so forth. All practical topics, really. And that's why the last one was really a practical lecture. And now we have to proceed a little bit more to conceptual lectures to make your knowledge of clouds a bit more comprehensive. And this brings us to Docker and container management. Still a very applied technique. You will find that every cloud out there, from AWS up to MS Azure, from Alibaba to Uber Cloud, to very specialized cloud office like Uber Cloud, for instance, you will find these techniques. And they were always a little bit behind the scene. We have seen that already when we talked about MapReduce. I was giving a short example but also in deep learning, this is relevance, which we will learn today. So it's something which, when you go out of this course, you should know that Docker exists, that Singularity exists, which is an equivalent, basically often more used in high performance computing in data centers, perhaps. But also Docker has really stand the test of time and is a so-called de facto standard for container management, for container deployment. And there are a couple of other techniques and other tools really that go alongside Docker. Kubernetes with kubelets, there's the certain Mesos component to it, and all of that will be a little bit looked at. And of course, we will compare the situation with Docker to typical virtualization that you already know. So what is the benefit now of, let's say, do container orchestration to do containerized applications versus virtualized applications only? We will also learn that it makes sense to combine that for let's say, high-low workloads in data centers, of course. So the first part will be really understanding Docker and container management. So this has to do something with the large cloud offerings, lots of services, and the Docker container examples will have the beautiful idea of bringing software really pre-deployed together. This pre-deployed and pre-installed notion you have already heard with virtualization. So in a VM image, so what's the difference really between containers and VM images? So what is a container Docker file? So we will look into this a little bit. Of course, in this course, we always talk about, deep learning, machine learning on a parallel and scalable way to really, let's say, leverage big data where it really makes sense and where you really need cloud computing resources and high performance computing resources. So I'll give you some examples of PyTorch in context, which is a deep learning model framework we didn't look at so far. We focused on Keras and TensorFlow. PyTorch is yet another one, which is also actually very often used in practice. There's a huge container service landscape, not only in AWS. I provide you this as a walkthrough a little bit, but then we will have some application examples. But you will see when you go to Google Cloud, when you go to MS Azure, and I brought you here a little bit also a short movie about this, which I found is very, very good to look at. You will see that this is really something which is broadly understood, basically offered in all different, let's say, clouds today, and a certain type of, you would say, de facto standard today. So you can take with any chance, basically taking here Docker container and rolling it out at MS Azure, and you have really a high chance that this Docker container probably is also running in AWS, right? So this gives you some portability benefit, which is quite good. And of course, if you now think about a company which has, let's say, a big, let's say, service landscape with different services together, you immediately think about different containers have to work together at different certain amount of times in the software lifecycle. So we need something like tools like Kubernetes really managing a cluster, which we will look at in the first part as well. In the second part, then we turn a little bit to advanced container concepts. Again, perhaps containers today could easily fill 5 to 6 lectures. I pick here, of course, because we have just one lecture essentially in this cloud course for it, just some highlights where I think they show very interesting, let's say, unique selling propositions of certain clouds or some interesting, unique functionality. So we will look into the Google Cloud, what they do in terms of deep learning, which is quite interesting, but also very specialized offerings of the IBM Cloud and Alibaba. Alibaba is a cloud we didn't previously looked at. So it's also good to check out these like IBM Cloud and Alibaba, because they're a bit different than AWS and MS Azure. Still yet, of course, have very similar solutions for software. Then Uber Cloud Containers is a very specialized way of looking for engineers, what cloud computing can do for engineers. We will have the computation fluid dynamics as one example of this. And then, of course, we look also a little bit more into solutions like Singularity, Mesos, what is, let's say, around this container concept as well when you think about other solutions. So a very interesting lecture. It will be, let's say, also very important in terms of practical insights when you go to an interview. Let's say in this domain, you really need to know these days, what are containers? What are containerized applications? And it goes all back to the services, because in the end, that's what we want to do in the cloud, right? We want to use services, we want to offer services. And we learned that this is very nicely done with virtualized resources. However, we also learned that, okay, in order to do this, we actually have to bundle together lots of different software. And this is not, let's say, just for putting everything more easy. It should fit together. We talk about that this runtime that you have there should be really consistent. It should be working together. You don't want to reinstall some software. You remember this AWS compute instances that we had in EC2, where all the deep learning packages, all the underlying libraries were already pre-installed. Very beautiful. You can directly start coding machine learning. And of course, usually when you basically have to install it your own, it's lots of different time. And so don't underestimate the time it takes to have all the dependencies, the configuration of all the software bundles very good together. Now, immediately you would think, okay, why we need containers then, right? So when actually virtualization gives us all of that, so why we do the pain of having containers? And of course, this first part of the lecture should really bring you the idea so that at the end of this lecture, you know why. But if you want to have a high-level summary, you see a little bit what this is going to. You have the container benefits on one side and the virtual machine benefits on the other. We can still claim that virtualization and containers really have a consistent runtime. That's their goal, and it would be strange if not. And also this application sandboxing is very good understood in both of them. So essentially a container can be, single, working on its own, and also you expect that from a VM image. It's actually also should run on its own, not with other dependency. We call that a sandbox, so it works in their own sandbox, the application. Now, when it comes to more additional benefits, you will see that a virtual machine in one way or another always carries around this operation system in a way. So containers, you will learn, don't do this. So they have a small size on disk, which is this essentially alluding to. And also the handling of whole hypervisors and virtualization usually comes for a certain price of overhead. You remember you have to install hypervisors and so on. And in this way, you have a more lower overhead if you do containers. Just having, let's say, in the Docker environment and a Docker file that then is actually getting all the necessary software for you. And this is something what we will now learn step by step when we go basically into the first part of this lecture. So first of all, Docker is really open source. That's the beauty in it. It's, as I said, in a way, a de facto standard today. No matter where you go, Docker will be chance to be supported in data centers and clouds, even in Windows or Linux environments. So this is essentially an understood technology. And there's a complementary, let's say, approach to it that is called the Docker Hub, which is more a marketplace or a kind of community really, where you find here as an example, lots of installed Docker images already that you can beautifully reuse. And you see as an example here, Hadoop data node, Hadoop slave, which is in a way more the Hadoop worker node, and name node, things we discussed actually in lecture 5. So here you have a pre-installed and pre-configured setup really of Hadoop that you can just deploy by using this Docker containers. And this is something where basically you save a lot of time of having the general installation. You of course want to modify that every now and then. You want to have different, let's say, IP addresses, for instance. You would have maybe different namings or different number of data nodes or essentially name nodes. But in the end, you configure it yourself. And you see really in the number of downloads that this is heavily used, like 1 million downloads, 5 million downloads, and so on. So this community is very strong behind this. And the Kubernetes, which we will tackle later in this course today, is then the idea of actually having all of these containers together looked at and orchestrate them. So meaning in a way of automatically deploying this application that you want and to scale it up and to manage it in its lifetime. We have seen, especially so in one of the PAAS lectures, that software lifecycle management can be quite complex, different versions. And if you then have different software containers working together, it is important that you orchestrate them. And the Kubernetes engine not only can do this very well with Docker, it is also, you would say, another de facto standard in the cloud. So chances are, if you have a Kubernetes basically setup of your cluster, which is also open source, chances are you can port it from Google, you can port it to AWS, you can port it to MS Azure, and so forth. So again, Kubernetes clusters based on Docker images is a kind of automatic way how to configure those software management today, and which is very important to know about. Hence, we look at this Docker tool a little bit more in detail. We talk about this, that it's essentially just containerizing an application. And if you want to have an analogy, I think the best idea is to imagine the big ship, right? Some smart people at some point in time thought it might be good to agree on a certain container setup. No matter how we transport it, let it be Smyrl line on a truck, let it be this Maersk line here with, let's say, thousands of these containers on a big ship going through the ocean, going on a railway, putting those on. The important thing is these are all, let's say, containers that have a certain standardized way to the outside. What's happening in the inside, if I do it for my moving apartment stuff, if there's lots of fish inside for Smyrl line, who cares? So the important thing is that basically there's a certain way of handling those. You can take a crane, they're always basically nicely fitting on the back of a truck. So in a way, what you want to do with containers and Dockers is exactly the same way. You have everything you need in these containers, right? And these containers have a very well specified way how to handle them. They contain lots of it, of course, for software, not for moving apartments or for transporting fish. Here we're thinking about applications, software. So what is the runtime? Where is the source code? What system tools and which libraries are really neat? Data is in data science is specifically important. So we talk about prepackaged data sets inside these containers, which is incredibly often used. In a way, you enable lots of flexibility. You have a certain amount of portability to say it is actually working between all the different cloud vendors very much. So it's almost like a standard. It's not really an official standard, but towards, let's say, de facto standard in the community. And basically, you will find this in the open source version for free, but also really commercial enterprise Docker versions. And it's basically also the basis for knowing, very, let's say, niche market offerings, like we will see a little bit in the second part of the lecture with Uber Cloud and engineering. And the key idea how that works is a little bit explored here. Essentially, you have this physical service that we already know from virtualization lectures. We would have an operating system on this, and usually there would be a hypervisor, but here we're talking just about the Docker engine. And the applications could be also then manifold building on this Docker engine where all these containers now come in, right? So think about this as being some of these containers on the ship, and as also this, let's say, interesting logo alluding to, is very flexible, can be stacked, can be used together very neatly. And if you have this, the immediate question is now, what's the difference? What is the difference to virtualization? In a way, we had this already. So Morris, tell us something new. And what you have generally as a problem is that virtualization is allowing you very good things, but in the end, you have a very high storage footprint. This VM images usually not only include the application, it includes really binaries, lots of libraries, and the entire guest operating system. You see that a little bit on this, let's say, comparison, right? When you have the infrastructure, which you of course need in those, let's say, deployments, you also need a host operating system. Without an operating system, you cannot do anything with, let's say, pure hardware. But of course, on top of that, we had this hypervisor, and then always this big bundle of guest operating systems which goes alongside it. So it's a Windows, is it a Mac, is it a Linux or Unix derivative of some sort? What we want to have here is to think about that this is maybe not really needed. Instead, we want to combine the power of this virtualization of saying these applications, binaries, and libraries prepackaged, perhaps also including data sets. But we want to do this in a more, let's say, standardized fashion of describing that all. And with this, you have these containers which enable more kind of low storage footprint and also being completely vendor lock free and away from all this guest operating systems, Windows, and so forth. So you have a kind of as usual, container setup, which all dependencies are in, it can run isolated everywhere. So in other words, you put it on the ship, you put it on a truck, you put it on the railway. It doesn't matter as long as the Docker engine is basically supporting it, right? Which reflects here the standard size of these containers so that you can transport, let's say, many of them, no matter who is actually, is it a IAMScript container? Is it a SumScript container? Is it a Smirline container? You don't care. They actually have the same standard. And with this, you come to a little bit of a vendor independence now. You can run this Docker images very nicely on different infrastructures. And that's the beauty of it. Some examples for you from the platform as a service example we had already in one of the lectures where I said we will learn more about these containers. Here, the Google Cloud is a very good example of the Google App Engine, enabling the whole software development cycle that we learned in lecture 9 to be supported by containers. There's a container registry, which is nothing else essentially than a private Docker registry, which enables you then also to store your Docker images within your cloud and then actually deploying it with other elements in this that we learned with Cloud Build and so on your cluster in order to support your software development lifecycle in the cloud, the different versions and so on we learned from lecture 9. And underneath is really the same idea of these containers running and managing them. Then when we look into the AWS services landscape around containers, you will see many different ones. I give you some examples that you see here in the list, and we go one by one shortly through it. But I think you immediately guessed the story, the idea, the story really behind it. So all of them have an added value in a particular sense, and we look through them. The first is, of course, this Elastic Container Registry, which is a container registry that makes it simpler. We know that already, so it's pretty much like the Docker images that we want to use. And if we do this here in the Amazon way, you can run these containers, really pull them out, have different version control to it, and manage the whole image lifecycle on this. You run these containers, and then for the runtime, you really can choose from different options. You would have this Amazon ECS service or the EKS service, so Kubernetes, or a pure, let's say, EC2 cluster. And these are different options, which is a typical power of Amazon. So it nicely combines their different services, right? But here, of course, it's a kind of foundation really to have this registry, because there's what you put the Docker images in order to, write code and package code, put data in, and then you deploy it essentially on some of these computing entities later. In order to do so, you have many different options, and I show you some examples here how actually production software is using that. Ubisoft, you probably know from some games, but also GoPro is very known for the camera you put on your helmet, of course. Now, how they use it is using the container registry, as we discussed, of course, as a prerequisite, but then you have different options. Here's an example of how those actually try to really build on an application called AWS Fargate. And the interesting element with this Fargate is it's very similar to those that you know from EC2, right? The computing. The containers should be then running on typical computing, let's say, resources. But while in the EC2, you really have to, let's say, organize it yourself. You have to look at which instances I need to do. You have to manage, let's say, a little bit of cluster and so on. In AWS Fargate, all of that will be, let's say, managed for you. So you don't have to manage all the services. And this, of course, enables that you can quickly use this infrastructure without any manual resource provisioning, which is beautiful for, let's say, companies like games, for Ubisoft, that just can focus on their game design, on their making their game better instead of thinking about large scaling infrastructure, IT, cloud computing. And that's why they're using the services. And also, of course, GoPro. And you see the impact that they're doing, not only enable multiplayer gaming of scalability. Here, GoPro uses it, for instance, to reduce its compute footprint by 70%. Because all of this is, of course, also elastic. It depends on how many people it's using. And this is, of course, a very much powerful services of AWS, as we know already. You can do still and choose to take the Amazon EC2 that we learned already in lecture 4 and 8. So pure infrastructure as a service. You actually build your own virtual machine infrastructure. Then you see here a Facebook example, essentially for cooking, which is called Cookbed. So here you have basically the right set of Docker images already ready. And here's the idea that you basically tag images, so you upload them. You see that a little bit here. What could happen in a typical application by using deep learning, for instance, of course, you have still this deep learning modeling of image analysis from cooking recipes, from, let's say, tagging here chicken, maybe something to do before. But once you have basically put that in this kind of application-oriented setup, you can put it in a registry, all this, let's say, code that you have, and then pull it every time you basically deploy this application. And by doing so, you enable applications like here, you essentially upload the thumbnail of any type of food, and essentially will go through the deep learning pipeline, will basically classify the thumbnail, and then you basically get out of it essentially what you think, what type of recipe that might be. And with this, of course, it's basically enabling scalability. It is an automatism. It's a really app that maybe you want to download and check. I'm not actually paid by that, but you know that is one way of how to do basically deep learning and having a niche product. Also think about that after certain TV shows and apps introductions, which is often used in these areas, it should quickly scale to the number of users, but also to the number of photos people is uploading. And then you really have trouble if you don't make it in a, let's say, scalable way. And here you really have an idea of containerized solutions, really, of using that essentially in production. And of course, you can imagine I can go on and go on with different examples. When you combine this, let's say, in a data center today, you will also see that, of course, in practice, you're mixing these Docker really with traditional virtual machine images. You can see that, of course, a data center has to be very flexible. So you find here some applications that require Docker engines, but of course you also have to serve those users which have traditional work VMs. So for this, you basically maybe also put that on a hypervisor infrastructure using here combined essentially still the traditional VM approach, but combining it even with Docker. This is enormous flexibility. And of course, we have to satisfy the customer in the end. And this is, of course, very important that to do so. But by managing all of this, think about now the big ship analogy that we have here. So how we manage all of these to do this properly on a cluster on large scale, we need a tool which is complementary called Kubernetes, which is an open source container orchestration tool. Here you see the benefits that it will actually manage the cluster for you on so-called kubelets, where essentially all the different service controllers can here, steer different Docker images, can pull different Docker images instances, really. So once you pull these Docker images, once they are installed and running, you can monitor them. And of course, you have, again, a master worker setup, really, where you have also, of course, monitoring if a service is down, if you have, let's say, scaling issues, so you have to deploy more of those for some certain type. So it really helps you to schedule all of these Docker images on various nodes like EC2, but also, as we have seen, when you use Fargate in a more automated fashion. And this is, of course, a specific service you find in the Amazon portfolio, this Elastic Kubernetes service that can use either Amazon EC2 or AWS Fargate, as we discussed. But here you have really, let's say, a provisioning of a cluster in between, which makes it, of course, very scalable for really big workloads in an automated fashion, which is really powerful. So another service that you basically can use, which is very powerful, and another deep learning application is just here using these services, which is a PyTorch deep learning examples. You have, again, the same model training idea. Once you train the model, you want to do maybe something like a Torch Serve, where you have a model ready for inference, very basically using this real, client applications using this model daily. Then you want to think about an automated process of doing so, putting it essentially in a worker node and be flexible and actually scalable by putting this in the AWS cloud, using then this EKS service control pane, which enables you also to add more Kubernetes worker nodes if we see that essentially the system doesn't scale, if basically many people now suddenly use this torch service, your specific applications. You can imagine Pinterest, if you know a little bit about it, has lots of images, basically 3 billion images is a good example, 18 billion associations between. So this is something where scale is really requiring an automated setup and also scalability, which you then have in the Kubernetes server that essentially can deal with this. How that looks like is a little bit also here. You have, again, worker processes, very similar that you know from MapReduce, from Spark, which has then, of course, to deal with the scalability and using very much the same principles that we learned already with master and worker nodes. At the end, I just want to summarize a little bit this notion of microservices. And as I said, you could easily talk about 5 to 6 lectures alone on containerization, but this video just essentially gives you a little bit of kind of business idea how you combine Docker, how you actually work out in the services. So that's why I found beneficial to look at this, even if it takes a bit longer. So enjoy the video right now.
Now that you have a good understanding of virtual machines, it's time to turn our attention to another one of the compute services, which is containers, which has grown a lot in recent years with the rise of Docker as a standard for a lot of the industry now. And what are containers? Well, essentially, it's a standardized packaging for software and dependencies. So think in a virtual machine, I typically have my operating system, I install my packages on, I install all my dependencies on, and I try to make sure that configuration works. With a container, I kind of pre-do all that work, make sure everything works together, and then when I want to run it, I just schedule it to run on a machine that's capable of running Docker containers. It's also a way to isolate apps from each other, and it works across both Linux and Windows servers, and allows separate apps to share the same OS kernel. Now, what's given the rise to this? And ultimately, it's application modernization, because there are a lot of issues with monolithic applications. If we install all our application code into a single server, minor code changes then require us to do full recompile and testing. The application becomes a single point of failure. Let's say one of those boxes there, the different colors you see on screen, one of those pieces goes wrong, well, potentially it takes down the entire system, and the application is difficult and often expensive to scale. So the answer to this is to break it apart into what we call microservices, where each service is its own individual application, if you will, and can be scaled separately. There's this concept of 12-factor applications. You make the app independently scalable, stateless, and highly available by design. And it helps to compare and contrast these, because when you think about monolithic, well, it's very simple to deploy. Inter-module refactoring, vertical scaling, technology monoculture are some of the themes we see there. When you look at microservices, it's all about partial deployments. Again, deploying the piece of the entire application that I need as needed. Strong module boundaries, horizontal scaling is the big difference. So with containers, and this is something to look out for on some of the exams, is if I want to scale out horizontally, containers are very, very good for that, because I can just scale out that particular service that I need to, as opposed to with monolithic, again, if typically, somebody comes and wants to scale the application, you just add in more CPU, add in more memory to the virtual machine to scale it. And the other big thing with microservices, it allows for a diverse set of technology, from a stack point of view. Let's then look at some of the keys to microservices. First of all, we have functional decomposition. As you can see by now, all those services tightly coupled together that are error prone become individual services. That's the first part of everything. Then we look at horizontal scale. Scale what we need to, not what we don't. This could mean that for virtual machines, if we've got an application that's a mixture of services, we scale the virtual machines horizontally in a scale set. We could scale the containers. We could use serverless functions. We can kind of choose what we want to use there. In addition, now we can choose to decouple the data much more efficiently. I can pick the best database for the service. So if Service 1 would make better use of Oracle, we can do that. Service 2, Azure SQL. Service 3, Redis. Maybe Service 4, we've got Azure SQL there, but it could be like MongoDB or Cosmos or something like that. So you can really start to see the benefits that containers provide, in addition to just the speed and efficiency. When you deploy in a container, they deploy very, very quickly when compared to a virtual machine. They're up and running very quickly. And again, they're not as error prone because everything's been tested. All the dependencies are coupled together. So when we deploy the container, we're good to go. So to drill this home, let's look at containers versus virtual machines. Well, again, on the left, if you remember from the virtual machines module, we have our hardware on the bottom, our hypervisor, and then we deploy the operating system and application in each virtual machine. With Docker containers on the right, we still have our server, so that's our hardware. And now that could be running, say, VMware or Hyper-V, or it could be an Azure virtual machine before it gets to the operating system there. So again, the operating system here is like Windows or Linux. Then we run the Docker engine on top of that, but now we can just deploy our application. So you can see we're scaling and scheduling the applications. We don't have to keep scaling out that underlying operating system. That's not to say you don't have Docker nodes underneath that scale out to support the applications. That's obviously got to happen. We have to have enough CPU, memory, etc. to kind of make all the magic happen. But once you've kind of figured out how to manage that service, and things like Azure Kubernetes service make that very easy, now you can focus on the application itself and scaling that out.
All right, so I hope this video, although it was a bit long, summarized really a lot for you, how it is done in business today in practice using containers, but then also the kind of notion around it with the microservices, which would easily fill probably 2 more other lectures, and which are probably much more taught in software engineering, how you do this today to enable individual services more and better maintainability, and so on, the benefits you have seen. So that's all for the first part of the lecture, and we return essentially in 10 minutes for the second part of the lecture.